All right. Good afternoon, everyone. Right on the dot. Thank you all very much for coming to my presentation. Today I've lured you into talking or attending a talk about Pokemon. But yeah, the project I'll be talking about is how to transform a Jupyter Notebook into a reproducible ML pipeline. Just to give a bit of an idea of myself, my name is Rob. I'm from Utrecht in the Netherlands. I used to be a developer advocate for Iterative, although I was caught in layoffs a little while back, sadly. And important for this talk, I'm a water Pokemon trainer. So a while back in Eindhoven, I was talking at PyData, and there I presented a project to create a machine learning model to classify Pokemon. And that led me to become the very best, like no one ever was. And from there on, I wanted to figure out, okay, we've done this. Can we do some other Pokemon-related stuff? That's a fun pet project that will also help showcase some cool technology. And that's what I'll be talking about today. So you'll probably have heard that Stable Diffusion and other text-to-image models are quite huge nowadays. So my idea was to create a pipeline with which I could create new Pokemon artwork and create some concept art for Pokemon for upcoming games. So that was the goal of the project. The approach would be to do a Stable Diffusion or use that as a base model, 1.5 to be precise, and train a LoRA to adapt the model into actually generating real proper Pokemon sprites. So for those of you who don't know, LoRA is an abbreviation for low rank adaptation, and it's the current beta in trying to, getting your text-to-image models to produce the best possible output. And the great thing about this is that you can train a relatively cheap and quick model that you just put on top of the base model. And that's something that you can do from your laptop. So I made the entire pipeline work on my local machine because it's cheap and because it's convenient. So the implementation, as I think many of you will do here, the first thing I do when I've got a data science project is to start working in Jupyter Notebook because they're great for prototyping. And if we move over here, I'll quickly take you through the notebook. So it's pretty straightforward. We do our imports and parameters. This is some housekeeping to find a project root. We set some of the model parameters. So here I'm interested in targeting all Pokemon types. I could also change this to water or grass or dragon. And here we've got some model parameters. So the max training steps or the max inference steps. For the model I'll be showing you in a little bit, I set this to 5,000, I think. And then some stuff for generation. So text-to-image works with text as an input. And this is where the prompt comes in. And as you can see here, we're using the LoRA that I trained in the pipeline. So then we need the diffusers repository from Hugging Face. We need to install the requirements and run a bit of config. This is all stuff you need to do once. Then I scrape the Pokemon images from the Pokemon website. So number one is Bulbasaur, and then Ivysaur, and then Venusaur. And those are the official concept art images. Actually, I think I can show you those right here. If we take a look at our external data, then these are the kind of images that we're interested in generating. Having done that, we can get a subset of a relevant Pokemon. So way up above, I showed you how you can set it to only do water-type Pokemon. For now, we'll just do each and every Pokemon. We need to resize the images. And then we get to the actual fun part, which is training the LoRA. So this is a bash command, and these are the settings. And as you can see here, I'm importing the parameters as I use them in the rest of the notebook. From there on out, it's fairly straightforward to set up the pipeline. So we take the base model, which is Stable Diffusion 1.5, and we then load the LoRA on top of the model. And then we can use it to generate images. So that's something I've already done here. And we can display those images. So this is the first result of creating a Pokemon that doesn't exist based on Pokemon that do exist. Is it any good? I'll let you be the judge of that. But to be honest, I'm quite happy that at least the art style is fairly similar to what we're getting from the actual Pokemon images. So if we then take a look at yeah, sorry, I already showed you this, the implementation. So these are the results for the same prompt if, and exactly the same settings if I only use the base model of Stable Diffusion. And these are the results we get when using the LoRa. So again, you can be the judge of whether these Pokemon are any good. But especially the first one, I think it looks like an Ekbaland, but it does reflect Pokemon to an extent. And this is how powerful LoRa can be, because with about 20 minutes of training on my own laptop, I get really different and really targeted results. I'm quite happy with these as an initial experiment. So then moving on, what I started doing from here was experiment to find the best settings to generate the best Pokemon. And in general, this is something you'll see time and time again in machine learning projects, where you just keep experimenting, you keep tweaking some parameters to get to that best Pokemon, or to get to the best predictions, or more general, to get to the best or the most performant model. And there's probably a few data scientists in the room today. This is what you'll be doing as a data scientist. You're tweaking parameters, you're changing data sets, switching back and forth to see if we can improve our models. Because we rarely get the opportunity to just produce a model and keep it in production. We have to experiment all the time. Even when we get a performant model and we put it into production, there can still be changes to the business requirements. We may need to change the context of our model. There may be some data drift. We just want to keep optimizing. There's plenty of reasons for us to keep experimenting. But experimenting gets real messy if we don't keep proper track of what's going on. So for the Pokemon images I showed you earlier, I can't recreate those right now because I don't know which precise settings I used when generating those images. And that's not particularly a problem for creating Pokemon sprites or Pokemon artwork. But it can be an issue when you're doing actually high-stakes model development. So maybe a quick show of hands. Who here has been guilty of keeping track of parameters and results in an Excel sheet or maybe even a physical notepad? I sure have. Like, that's most of the room, right? Because that's easy. You just go back and forth and you tweak some stuff and you write it down. But it's messy, and it gets even messier when you need to work together with your colleagues or your teammates yeah, on these types of projects. So a while back, I was in Berlin and I talked to someone. I gave a talk roughly similar to this one. And he actually told me that a while back he was the head of a machine learning team for a bank. And they put a model into production about 4 years ago. And someone from higher up came up to him and said, hey, you know that model that we had back then made some funny predictions and we're in a bit of trouble, so we need you to reconstruct what precisely went into that model. So which data were used to train the model, which parameters, which choices were made. And the entire team had to spend about 2 weeks of their time trying to reconstruct that model. Which is, it's not something you want to do. And the more models you keep in production, the more difficult this gets to keep track of. So that's why we need reproducibility. And it's not enough to just track the model and track the results, because then you know what the outcomes of your experiments are. But you can't reproduce the experiment. And just like in science, in data science, reproducibility is very important. So what do we need to do to get to full reproducibility? If we want to get there, my pitch to you is that we should define an experiment as a specific combination of data, code, and parameters. Because if you have those data, code, and parameters, then you can rerun your pipeline, you can rerun your model training, you can rerun your predictions, and get the same deterministic outcome. Or at least that's what we're aiming for. But this is quite difficult to do, or at least for some of the parts this is difficult to do, because for code this is very much a solved problem. If we look towards data engineering, or more broadly software engineering, then of course we'll have Git to keep track of our code. And Git works really well. You get a tree, but it only works really well if your file size is relatively small. So it's great to keep track of changes to text, but maybe less so when you're trying to version your data sets. So could we have something that's Git for data and that defies the 50 MB size limit in GitHub? So some of you may now think, oh, you could use Git LFS for that, and that's true, but Git LFS requires a separate server, and I'm here to pitch a product that doesn't require that, which is DVC. So remember how I told you that I used to work for the creators of DVC at Iterative. Take that into account. That's my full disclosure to you. The good thing is DVC is fully open source, so you can give it a go. And they laid me off, so I'll be giving my honest opinion here. DVC, its namesake is data version control, but there's a little more than that. Its main features boil down to three components. So you've got data version control, pipelines, and experiments. And I'll now go through those three components and then show you an implementation of a pipeline made in DVC. So first, the data version control. This is a Git repo, as you may recognize it. So we've got our list of commits. And in a given commit, we have a data set of Pokemon images. So here we see Chansey and Lapras and Caterpie. And those are part of a Git project, of your repository. Now, those images, we don't truly want to track in Git itself. So if we start using DVC, we run DVC init, and we replace the physical images with a metadata file. And the metadata file, the dataset.dvc, contains a hash for the images, the size, and some other information, the number of files. And it points towards the DVC cache. And the DVC cache is where the physical images are actually stored on your file system. So here you can see that the images got moved to the DVC cache. Their names got completely scrambled up because they're now hashes. And we don't want to keep track of that manually anyway, so the DVC cache may look a little odd if you actually dive into the file system. But DVC handles the translation between the metadata file in your Git repo and the files in your DVC cache. And now the beauty of this is that if we create a new commit, so here you can see that the typeface changed, so we've got a new data set that points towards a different specification in the DVC cache. So here we removed the bottom Pokemon and we added Ampharos because we're now apparently in generation 2 of Pokemon. And the other two Pokemon are still part of the new commit. So Chansey and Lapras are part of both commits, but they don't get duplicated in the cache, which saves you a lot of time, storage, and also money. And then we have this cache, which lives on our local system, in my case, my MacBook, and we can mirror that to a remote storage, which can be an S3 bucket, a Google Drive, an SFTP server, anything you'd like it to be. So once we mirror that and we apply the same basic principles of versioning our data as we do for code, we can start using that in some more interesting contexts. So we can just do data versioning, but DVC can also sort of automate that based on pipelines. So this is the setup I showed you earlier in the notebook, roughly. So we've got cohesive steps of code. So first we set up the diffusers, then we download the Pokemon stats, we scrape the images, we resize those images, then we train LoRa and we generate the text to image. And if we go from top to bottom, much like you would in your notebook, then you get your results at the end. But each and every one of those stages produces an output or multiple outputs. So here we see, for example, that the resized Pokemon image stage creates new Pokemon files of a new size. And if we specify those outputs, we can also use them as dependencies for downstream stages in DVC. So if we then tell the train LoRa stage that the processed Pokemon directory is a dependency, then we can make sure that the train LoRa stage only triggers once the images have been resized and placed in the processed directory. And what's great about this is that oftentimes you won't change all of the stages at once. So for example, if I change the train LoRa stage, then that doesn't affect all of the above stages. And we don't need to rerun those, and DVC can cache the outcomes of it, and thus speed up your model training. So we can then restructure this as a DAG, where each of the stages is dependent on the outcomes of the stages that preceded. So that's pipelines. And then we can start using that pipeline to run experiments. So this is our pipeline where we do some stuff, and we've got inputs and outputs. So the input is the code, the data, and the parameters, and the outputs can be the model itself, but maybe also some plots and some metrics, anything that's the result of your model training. And as we discussed, we want to version each and every one of those components with either Git or DVC. So as a rule of thumb, small files we version in Git, and the larger files, such as the images or in the model itself, we version with DVC. And if we do all of that together, then we can consider one pipeline run as an experiment, or more technically speaking, as a Git commit. And now if we want to go back through our history to find our previous experiments, we can simply do a Git checkout. So here we see that the parameters changed for one of the previous experiments. The other stuff stayed the same, but because the parameters changed, we've got an affected model, plots, and metrics. And with Git checkout and then DVC checkout, we can quickly pull up those results. So implementation number 2, this is where we get to the fun part, the code. So I will pull up VS Code. Is this big enough for all of you to see? Good. So let's take a look here. We are in our virtual environment. And the first thing I did, so we have the notebook. It's still here. I could remove it at this point. But I split this up into separate Python modules. So if we go to SRC, for example, we've got these great Pokemon images. This has got precisely the same contents, roughly, as the notebook, but with some more boilerplate so that we can run this module from our command line. So if we then use that command, we can use that command in a DVC YAML file. So these are the stages as we showed them earlier. So we've got set up diffusers, then scrape Pokemon images. Let's scroll a little bit down. So for example, the resize Pokemon images here simply runs this command. So it's a Python 3 script. It runs resize Pokemon images.py, and it passes the parameters from the params.yaml file. And in DVC, we can also specify our dependencies. So that's the existence of the Python module, but also the existence of these files so that we don't get file not found errors. And it's got a number of outputs that are the result of this stage. And then we pass the parameters, which are parsed in from params.yaml. So here we have our overview. We can change our seed, we can change our learning rate if we want to train it, we can change the max amount of steps. And then with these two combined, we can run the DVC pipeline from our command line. So for example, let's change the seed of our image generation. So we're at PyCon 2023, so let's change it to that. I think we'll be fine just generating now maybe 3 Pokemon right now. No, sorry, this one. And we'll speed it up a little by doing fewer inference. Yeah? Yeah, okay, cool. Thanks. So if we now do DVC repro, which stands for reproduce, we can, oh, hey, there we go. We can now use DVC repro to reproduce our pipeline. And DVC, as you will see, it has cached the underlying stages, so it's skipping those, and then picking it up where we generate our text to image. And we can see the images come in our outputs folder. It's going to take a little while, so a few steps. Should have triggered this while the mic was off. There we go. And this one returns an entirely black image because apparently Stable Diffusion thinks that this is not suitable for work content. If you've been around the internet in the past few months, then you will have seen that Stable Diffusion and other text-to-image models are broadly being used to generate not suitable for work content. They are trying to combat this. But yeah, you also get some false positives. So this is the first result. Don't know what type of Pokemon we're looking at, maybe Steel. maybe dark, could be ice, I don't know. But yeah, fairly happy with at least the art style. Oh, this one is quite good. It's got eyes, it's got an appropriate amount of limbs. I think this might be Flying Grass. If anyone wants to pitch a name for the concept Pokemon, hit me up after the show. So we've got our 3 images generated, and now we could do a git commit. Oh, there we go. Git commit, message. Oh, sorry, I should do git add, of course. Thanks for the tip from the audience. Git commit, and generate Pokemon with 2023 seed. There we go. And then we could push that to our remote. And now if we take a look at our git log, we can see our different commits that we generated. So I'll run a few of these experiments before coming here. So right now you'll see that, first of all, params.yaml has the seed that we specified, and the images are here. Now, if we go back to one of the experiments that I ran earlier, so for example, the seed with, let's take this one, seed 1500. So quit, and then git checkout, and our hash. Then we can see that params.yaml has been updated, and we now have the seed from the previous experiment. Now, as you'll see that the outputs still haven't changed. And that's because those are tracked by DFC, so we also need to run DFC checkout. And if you'd like, you can automate this, that whenever you run git checkout, DFC checkout gets run as well. So if you do DFC checkout, DFC retrieves the images from its cache and has some of the Pokemon that we created earlier. Also some fun ones here. Let's see if there's anything else I would like to show. I think that's the most important part. I could quickly show the DFC cache. So here we've got the cache, and as you'll see, it's split up in nonsensical directories where we've got files based on the hash, which we can't show here. Then, if you're a user of VS Code, you may also be interested in the DVC extension for VS Code. It's not the most useful here because our results are images that are outputs, and it's difficult to grade those. So we don't get an automatic score to see how each experiment performs. But if you do, so for example, if your target is an F1 score, then you can specify that as a metric, and we can compare those experiments in our experiment table. So for example, we can see what parameters we changed, and then which metrics are the result of that. And from here, we can also run new experiments, for example. So yeah, that's a more visual approach to what you can also do on the command line. So much for the implementation. Then the recap and takeaways. I hope this has been somewhat insightful. The takeaways I'd like you to take home is in data science, we experiment constantly. So we rarely get to just put a model into production and leave it there. To do proper experimenting, we need reproducibility, because otherwise we're just messing around. Much like science, you need to be able to reproduce your results for them to have any value. And Jupyter notebooks are great for prototyping, but not so much for reproducibility. Sorry, I don't think I actually highlight this, so let me just, I've got a little bit of time. Why Jupyter notebooks aren't great for reproducibility. First of all, whenever you run them, their metadata data changes. So you'll get a completely new file in your Git repository. And there are ways to mitigate that, but it's just not a nice way of working. Also, you can jump back and forth arbitrarily between cells, which makes it non-deterministic. Yeah, and the file size can get quite large in notebooks. Again, I'm really not bashing Jupyter notebooks. I think they're a great tool. But once you get to the point where you have a working prototype or you have something that you're happy with, and you want to quickly run successive experiments, my suggestion would be to move over to a pipeline, which you can run with a single command rather than clicking through the cells. So that full reproducibility we can achieve with a combination of Git and DVC, and then we can track the data, the code, and the parameters. DVC is then used for the data version control and the pipelines and the experiment management. That concludes my talk. Thank you very much for attending and for your and for paying attention. I hope you take something away from this. As I mentioned, I'm open to work, so hit me up if you've got an exciting opportunity as a developer advocate. I've got a few further resources. So the easiest one is to go to robdewit.nl, my personal website, and the slides are there, so you can take a look at the further resources. The other one, dvc.org for the docs. And dvc.org/chat for the Discord community. They actually do the community part really well, and it's easy to get help if you're starting out. And you'll also find a list in the slides of all the sources I used to create this project. Thank you very much.
Thanks for watching. If you enjoyed this product update video, please like and subscribe. Thanks, Stevie. And feel free to post comments and questions below. Beyond our tools themselves, we have many resources for you on your ML journey. Visit our docs, our blog for tutorials, our YouTube channel, our Discord server for support and community, and our free online course. You can find all the links to these resources in the description. Thanks for making it to the end. Devi and I will see you in the next video.